So for this video, we're going to be calculating the part 2 of the video. So we're going to be using closure. We're going to explain out. We're going to explain and code a higher order function that returns functions that calculates a Fresnel array, the tangent and normal vector for the helical curve. We're also going to explain how the radius curvature can be obtained at any point along the helical curve. So the Fresnel array is just describes the properties of a particle moving along a differential curve, which is our oscillating coil that is going around the tangent and normal vector of our axis. So what we're going to be doing is we want to calculate the Fresnel array formulas to get these values. So we're going to first calculate the tangent of the curve with respect to its arc length. We're also going to calculate the normal vector with respect to its arc length. We're going to create some functions, and we're going to call it. So the first thing we're going to do is we're going to define a function called mz curve, and then we're going to take in the values of the time, the radius, and the height. And we're going to want to put all of these inside the function. So we're going to put that, and we're going to tab it. And then we're going to also need to do J and P. We're going to want to do it with respect to the Jax function. So we can calculate the floating number. And then we're going to be able to call XYZ. And we're going to want to make it an array that takes in X, Y, Z in their different respective conditions. And we want to return it. And then since we need to redefine X, Y, Z because now it's undefined because we put it outside of the function. And then we're going to TR and MZ. And if you run this, nothing really has changed. We're just redefining a bunch of stuff. So now we want to calculate the curve of the Jacobian. So Jacobian. And then what we're going to do is we're going to take the function that we just made. What I like to do is for it to pop up so I don't have to write it. There it is. And then we want the argument. We want it to be 0 because we want it to be with respect to the first element of the function of the curve that we made. Because in the end, what we're trying to do is we're trying to make a coil go around this helical curve. So see, with respect to that, if we take the derivative, you can see that it turns into a constant. This goes to 0 and then 0, and we're left with t. And we're going to want to allow integer. We want that to be true. Beautiful. Okay, now what we're going to do is we're going to want to find the curve of the Jacobian that we just made. We want to find the values. Dot R Z. Beautiful. So we found those values. Oh God, I think I'm messing up here. So now we want to find the tangent of the curve. So the tangent of the curve that we were trying to find to calculate these Fresnel array equations and we want that to also be 0, and we want allow integer to be true. Oh God, should I press enter? Now what we're going to need to do is we're going to define the tangent function that's going to take in our three our time, our radius, and our thing, and we want to find the tangent of the curve, TRMZ, and then we also want to find the magnitude. And this one we're going to solve by solving the linear algebra, and then we're going to return v divided by magnitude. Okay, so now we're going to want to do that for the normal vector of the curve. So we're going to copy this, and then we're going to paste it. We're going to change this to normal of the curve, because we wanted to find the tangent and the normal vector of the curve for the Freyne-Serre formulas, but we need to also change certain values. So this one we're normal, and then this one we can copy that and we can put it here. And what this will allow us to do is find the normal values of the curve. So let's just find the RMZ, get some values. Okay, we got some values for that. Now let's do it for the tangent of the curve as well. Find the array of values that we need to calculate to get the Freyne-Serre formulas. Well, you need to be at a floating point number. And then MZ. Okay, so we got values for that. Okay, we don't need this anymore. We don't need this anymore. But we're able to find the values. So now what's left is we're going to need to define a new function, and we're going to name it Freyne-Serre, and then we're going to take in a function. We'll call that function f. It's important y, and then we're going to define a function, the f, with respect to t, that's going to take the Jacobian of that function f. And then now we're going to need to define functions to calculate the Freyne-Serre equations. Okay, so we're going to turn JNP dot linear algebra df with the function of t, and then we're also going to define the tangent that we were meaning to find. That's also going to take in the value t, and then we're going to return we're going to write the derivative of df dt t divided ds dt t. And then we're also going to need to calculate the Jacobian of that derivative. So we're going to use the built-in Jac functions, Jacobian, and then we're going to calculate the built-in function, and we're going to get the tangent. We're going to do the same for the normal, but we're going to make another function. And all these mini functions within this overall function should be able to calculate the Freyne-Serre. And then, return dt of t divided ds dt of t, and then we're going to return the tangent and the normal. Okay, so now the last part of the video we were supposed to explain how the radius curvature can be obtained. So we're gonna recopy this, so we're gonna be able to find those values. So we want to rename it, and we're trying to find the radius curvature that can be obtained at any point along the curve. So we're going to take the function t, and then we're also going to, okay, we don't have the radius because that was from above, so 3, what was it, 3 mz equals 0.4. And then we're also going to need to find the tangent normal Frene Serre, and now we're going to put that into the curve, and that should be able to find us what we're looking for. We're able to find what we exactly were looking for to calculate the higher function that calculates the Frene Serre, the tangent. We have the tangent, and we have the normal functions that we were calculating using the built-in Jacobian function. And then we're able to find a curvature along any point on the curve, which will be important for us when we're trying to create the